Welcome again. Today we continue to look at SN1 and SN2 reactions in organic chemistry, focusing specifically on the type of solvent that is used in SN1 and SN2 mechanisms. Here we have a tertiary halogenoalkane. In tertiary halogenoalkanes, nucleophilic substitution by the hydroxide ion nucleophile happens very efficiently when the halogen exits and the very stable carbocation is formed, being stabilized by this inductive effect from these alkyl groups that surround the carbon. Then this allows for the nucleophile to make its approach and to carry out the nucleophilic substitution, which depends on the concentration of this single molecular entity, the halogenoalkane. So this is how we get the term SN1. But to allow for this SN1 reaction to happen, it's important that the solvent is polar because you have charged entities in the reaction. But it's also very significant that the solvent is a protic solvent and that it surrounds this OH and keeps it in check to allow for the carbocation to be formed first of all, and then to allow for the OH to be released to associate with the positive carbocation. For if we did not have a protic solvent to surround or to hydrogen bond to the OH, and a protic solvent would be species like ammonia and water that form hydrogen bonds and surround the OH, making a shell around it to allow the carbocation to form and then slowly releasing the OH, meaning that the rate of the reaction is solely dependent upon the concentration of the halogenoalkane, which leads to the formation of this carbocation, which is described as the RDS, the rate determining step of the reaction. So very important in maintaining this mechanism is the type of solvent that we use. And SN1 reactions use protic solvents like ammonia, water, or hydrogen fluoride, species that have hydrogen bonding associated with them. With this kind of mechanism, it is possible not only for a tertiary halogenoalkane to undergo an SN1 mechanism, but it can also happen in a secondary halogenoalkane. But more significantly now, it's the type of solvent that determines whether the secondary halogenoalkane would undergo SN1 nucleophilic substitution, or if it might undergo SN2 substitution. In SN2 nucleophilic substitution, two molecular entities determine the rate of the reaction. And here, the rate of the reaction depends not just on the concentration of the halogenoalkane, but also on the concentration of the hydroxide. And in this case, it's really important that we have a solvent like propanone or ethyl ethanoate, something that is not going to hydrogen bond to the hydroxide, but leave it in a state that we refer to as being naked, so that it can immediately associate with the halogenoalkane and form this transition state. Depending upon the type of solvent, a secondary halogenoalkane can undergo both SN1 or SN2 reactions. Typically, an SN1 reaction happens in tertiary halogenoalkanes, and the SN2 mechanism happens in primary halogenoalkanes. But secondary halogenoalkanes, depending upon whether the solvent is aprotic or protic, they can undergo both SN1 or SN2 reactions.